remember that I will, first of all, we have a chat, and second, I will try to join each day 10 minutes ahead and sit here in this meeting room, so you have a chance to chat verbally, ask questions, and discuss something in a smaller group. So if you have something to bring up, join 10 minutes earlier. I'll be here for you. I'll be happy to chat and discuss both content of this class, any suggestions, recommendations, something else. And without further ado, let's jump into our second topic, which is networking in the cloud. And as I promised, there won't be any slides starting from yesterday. However, there are concepts that I need to demonstrate, and I will keep my promise. And we will do some live diagramming sessions instead. Basically, what I will do is draw together with you and at the same time explain what we what we will be building. So in AWS, network is sort of, I would say, your skeleton of your infrastructure. Exactly through network, you define high availability. Through network, you set up where and what will be landed, where and what will go. And to be capable of properly building a network in Amazon, we need to understand what a thing called AWS Global Infrastructure. So AWS consists of multiple regions. So region is the biggest, I would say, container that we can use. So yesterday we had US East. Also, there are like US West, Europe, Australia. These are completely different geographical areas. By geographical area in this context, I mean like either separate continent or separate part of the continent. For example, in case of United States, the region will be like, for example, Eastern US, Western US, Canada, so on and so forth. So within a single region, there are even more in like traditional system architecture. We could call it fault domains. What is fault domain, right? Imagine you are a traditional system administrator and something is wrong with the rack, right? Someone pull out the cord. This means each virtual machine in this rack goes away. Or imagine power goes out in your data center and you're out of power completely. This means like entire building and everything that was hosted in this building, in this data center, is no longer available. This will be your, I would say, several levels of fault domains. In AWS, there is a concept of availability zone. So basically, availability zone is a separate, distinct set of data centers which spans not like separate racks or even separate buildings. These are completely separate group of separate data centers. This means several buildings connected to each other through a high-speed network, and within this group, they might share power lines. Sometimes they might share buildings, but sometimes not. And different availability zones will be completely independent. Separate availability zones will be completely independent one from another. What it means? This means when something happens with the data center, something happens with supplies, electricity. I don't know. Maybe someone breached the data center and turned everything off. Only a single availability zone will go away. So in case of a failure, it only half of your infrastructure will be affected, either this one or that one, but it's very unlikely that both of them are affected at the same time. And if yes, this is definitely something serious, and there would be things more important to take care about. Within availability zone, you basically define your networks, you define your subnetworks. So you'll have a VPC, virtual private cloud, that's like a high level container for all your networking things. It will define your CIDR range, basically what type of IP address you'll use, and it will span multiple availability zones. So when you create a VPC, it automatically available in all your availability zones. After this is done, you will create subnets. And subnet, in turn, is something that should be either in one availability zone or in another availability zone. This means when you create your subnet, you precisely define in which AZ this subnet will run. This means to have high availability, we must have at least two or ideally three subnets. But that's only for a single layer, for example, like public, right? Also, we might usually what's deployed in public subnet is available to internet, and I will explain you in more details how it works just in a couple of moments from now. But also, there will be a thing called private subnet. This means something available solely within perimeters of your network, your VPN, within your VPN, or only from within this VPC. And again, one more time, I'll explain what is the technical difference and how we can change and how we configure them in just a moment. So basically, how to better. Okay, very cool. So when you create a VPC, you define a subnet, a VPC range. For example, 10.0.0.0, let's say /16. That's the biggest one that's available in Amazon. This means this /16 means first 16-bit, like exactly half of this number is dedicated to network name, and the remaining ones dedicated to everything within, to the host name. And similar for our public and private subnets, we will define our CIDR range over here. And it should be within, it should be smaller than our VPC itself. So it will be 10.0.0.0/24. This means last first 24 bits. This means these three first octets, these three first number, 10, 0, and 0 is our subnet name, subnet address, and remaining 0 through 250, 256 minus several hosts that are reserved will be for our host addresses. And it will make more sense once I demonstrate this in action after we deploy, after we write Terraform for that, and after we deploy it. So this one should be different. It should still be within 10.0 because we have first half for VPC, and subnet will be 1, and also 0/24. And within our same VPC, each subnet should have in case of 16 VPC and 24 subnet, this number should be unique. 10.0.2.0/24, 10.0.3.0/24. Now, what else we need to have for our VPC to work? And pay close attention here. Make sure you get this. And like when recording becomes available, make sure you watch this again and again until you fully understand this part. It's a very popular, for example, AWS interview question. What components we need except for VPC and except for subnets, right? So we'll start with a thing called Internet Gateway. Internet Gateway is an abstraction in AWS that lives within a VPC. It spans all availability zones at the same time. It's highly available by design, and it's a kind of like virtual switch, I'd say, in order for us to access resources on the internet, in order for our servers to be routable from internet, an internet gateway should be attached to your VPC. Also, we need to explain to Amazon how it should redirect requests and under which conditions the network request should remain within the network, and under which condition these should go outside through internet gateway to the internet outside of our VPC. And for these purposes, there are route tables. So we'll have one route table shared across our public subnets, and I will explain in just after these. There will be slightly different situation for our private subnets. So private subnets are not directly routable to internet, and there is a thing called NAT gateway. Basically, it's most likely some of you are familiar with the term called NAT. It's something you use actually on daily basis, right? When you connect to your provider, you are not receiving a public IP address, and you are receiving private IP address, which is in turn hidden behind the public IP of your provider. And this process of hiding this IP address and resharing single public IP address, is called network address translation. And in Amazon, you don't have to run your own nets. You can just have another abstraction called NAT gateway, which lives in your public subnet. Basically, it's a box like a proxy server, which intercepts requests from your private IP and redirects them into your internet at the same time through internet gateway. And also, our private subnets will also have their own route tables. But in case of private subnets, we'll have two route tables. Actually, no. We'll have one route table per availability zone. If we have 3 availability zones, we'll have 3 NAT gateways, 3 private route tables. Why is that? Because, as I mentioned previously, internet gateway is shared across a VPC. Does not matter if it's first availability zone or second availability zone. It will always go to the single point. It will always go here, and be redirected to internet. But in case of private, it should the request that's intended to be served outside of the VPC, the request that should go outside, should go through corresponding NAT gateways. So this private subnet have its own corresponding public subnet with its own NAT gateway. So if we were to have only one route table, this means both of these subnets should go either here or vice versa, both go here. That's why for private, we need two of them. Yes, and I think it's a good time to ask questions. Ram.
Hey Vladimir, I missed the last part of why we need to have a dedicated route table for private subnets versus. Can you explain that again?
Yes. So as I described earlier, availability zones means fault domain. Means if something goes wrong, most likely entire availability zone will go away. And let me show you this. So if we have a single NAT gateway and all our subnets, for example, go to this NAT gateway, right, through a single route table, what will happen? Sorry. What will happen if this entire availability zone will go away and we have a route that goes over there? We will lose our internet connectivity, right? That's why we should basically have everything that we need to establish entire communication line within a single availability zone. This means that we have our own copy of NAT gateway. We'll have a route table pointed to this NAT gateway. And route table, single route table, at the moment of time, it can be only attached to one subnet can have only one route table. And one route table can have only one route out to the internet. That's why we need two. But here, they are resharing same route, and this route is pointed to a single destination, which is internet gateway. Does it make more sense now?
Yeah, in terms of the private subnets, yes. I'm still a little bit confused, but I'll wait for the end of the class. See, maybe once you.
Okay, so probably when we start doing this, it will start making more sense.
Sure.
Cool. So what else we need to do? What else we need to have? We need to have an IP address if we want to connect to something, right? So, and there is a thing called elastic IP address, and it is either assigned to your NAT gateway, because like everything should have an IP address, or it can be assigned to an instance. So basically, we are putting a virtual machine inside our subnet. We need to select a subnet. You might ask why we haven't done this in the previous class, and the answer is that we use so-called default VPC, and the idea of it is that it allows us to quickly launch AWS services without having to deal with complexity of networking or with complexity of VPC. But if we want production-based solutions, we for sure need to be on board with the concepts of VPC, and we should be capable of building our own VPCs from scratch, and of course, obviously, ideally using automation. So just to repeat, main components are VPC, availability zone, subnet, internet gateway, NAT gateway, elastic IP, and route tables. Also, there are tooling for making firewalls, like security groups and network ACLs, but we will cover them later down the road. And without any further ado, we'll jump right into repeating the same architecture, but using Terraform. So precisely where we left previously, yesterday, that's our code. That's our terminal. So can anyone tell me what should we do first? Yes, Sanjeev.
Define the VPC resource.
We don't need to rush.
Pull.
We need to.
You're going to pull. You're going to follow the workflow.
Yes, like step by step. Piyush, yes.
We have to do git checkout main first.
Yes, definitely, exactly. We'll repeat this again and again because it's like really important until everyone grasp. Always, you can see here. Yeah, that's a hint. Task 2. That's the name of the branch. You can find out it if you don't have this extension using git status, right? It will tell you on branch and your branch name. You need to git checkout main. You need to pull latest changes, git pull. You can run git status again. It will tell you let me real quick change. There is no yet git ignore. Looks like I haven't merged my previous commit. Very good. We can fix this real quick. Terraform in 21 days. Branches, pull requests. Hold on a second. Yeah, now it works. This is what should we see every time before we start. It should say branches main, and there is nothing to commit. Working tree is clean. Let's create a branch, call it VPC, and only now we can get back to our code editor and start implementing. I'll have a separate file and call it vpc.tf. Into this file, all our VPC related things will go. And the first one is the VPC itself, this huge and big container for our networking things. Actually, no. Let's do this like in a minimal example. And you might wonder, how do I manage to remember syntax? And in fact, I don't remember syntax. And as I mentioned previously, being able to write code is not always about remembering things, but more about being able to find, of course, in exception for some like foundational basics, but you should be able to find any resource, documentation for it, and confidently navigate first of all, official documentation. So Terraform, AWS, VPC. We can Google this, and what it will give us is exactly this basic usage example. And we can scroll down and see all the possible arguments that we might be interested in. And ideally, again, when you do this in production, you should be able to read without rush, carefully, everything, information about each option, and make proper weighted decision about whether you need it or not. Now, basically, what we can do is actually, let's do one more thing. Let's, for now, just probably, yeah, we can remove this at all. We won't need this anymore. We'll just move forward with our VPC. So what I can do is run Terraform plan. It will tell us that it wants to create a VPC. Yeah. And let's run Terraform try and hit yes. This is something I was not expecting. Just a second. I couldn't find resource. Let's do one more time. Very interesting. That's, sometimes AWS itself, AWS API might behave in unexpected ways, maybe like delays, maybe API might like fail and not return anything from the first try. So yeah, that was truly unexpected on side of AWS, and from the second time, it applied just fine. So let me real quick log in into the AWS portal. We can go to VPCs and see our VPC created. But which one is which, right? So we might want to add some text to it, right? Just to find out which one was exactly created by us, which one was there before, and to be able to distinguish one from another. And if we don't really sure, if we don't remember what exactly to write, we can always get back to documentation. And either see this argument reference, full reference, or go and check some examples. So what I want to have is create some tag for it. Okay, let's hit save. Let's run Terraform apply. And hit yes. This time it modified our resource. And if we check it one more time, if we refresh it, it will put the name into this specific column, and we'll be able to clearly identify that this VPC is main. This is what we have just created. Now let's deploy a subnet. And the strategy is very similar. We can go and search for AWS subnet Terraform. Always try to open and understand the very first link it is giving. It should be from the official documentation hosted on registry Terraform.io. It's not really good idea to search these third-party blogs, because that's not a vendor, that's just an opinion of someone else, and very often it might be out of date. So always you should see this website, you should be capable of navigating the universal source of truth. So in our VPC, in our subnet, we'll need basically two main blocks. This is VPC ID, and this is our CIDR block. So let's just steal this example for now, and it is completely fine. And let's call it public. Now, can anyone tell me what this thing might mean? What it means? How we can decipher this code? What it leads us to? Yes, Ram.
Yeah, so it's like inheriting from that attribute from the class AWS main, and we are importing the ID. If we go to the EC2 instance UI, there is an ID associated with the AWS VPC.main. So in this variable VPC underscore ID, that ID of that main VPC ID will be stored.
Yes, very good, and that's exactly right. What we're telling it is, go find AWS VPC, which is called main, this one, and extract its ID automatically, like dynamically. We could have done it like this, for example, just copy our VPC ID and simply it is called hard code in the programming language, or in the programming terminology. This will, at this point, this will work just fine, just perfectly. We can run Terraform apply. We will hit yes, and it will create everything as we intended. One subnet is created. But when we run Terraform destroy, for example, and delete our subnet together with the AWS VPC main, what will happen? This VPC ID will go away forever. It will no longer be available. No more. It's gone. And when we run Terraform apply second time, it will still try to find this ID of this VPC which no longer exists. And say VPC ID not found, VPC with the ID that we specified does not exist. So what we need to do instead is explain to Terraform that, hey, we've in the same configuration previously created AWS VPC. We called it main, and we need its ID. And again, you can always go to the documentation and check attributes of any resource that you would like. Yes, attribute. You can, for example, for subnets, you can check its ID, its IRAN, its tags, and so on and so forth. So always make sure you don't have hard-coded values in your configuration. And let's run Terraform apply one more time. Now it created successfully. What else we need to do? So as I mentioned, availability zone should be specified. Otherwise, it will still create our resources, but then it will randomly assign your availability zone. So in advance, don't forget to include your availability zone. And availability zone consists of the region name and the letter code. So it will be, for example, US East 1A. Let's save that. No, well, I'll explain this later. And let's run Terraform apply. So we were lucky enough. These availability zones were randomly chosen even before we specified it to be US East 1A. But if we were to switch it to US East 1B and run Terraform apply, what will happen? So why it is saying that AWS subnet public must be replaced, and why it is saying that it will be destroyed and recreated? What have happened? Can anyone guess? Yes, Ram.
As you explained, that each availability zone will have a different CIDR range.
No, not CIDR range, something else. Someone else raised hand as well. Who was it? Sorry, I didn't notice. Yes, Ola? Yes, please. Okay, just in case we are not able to hear. Okay, anyways, let me explain this myself then. Each availability zone means at least separate building, or maybe even like separate town in the area. Which means if we deployed a network, a subnetwork, some resources in one building, and later we've chosen the different data center, different availability zone, this means it will need to destroy the resource in the old building and move it, or in our case, recreate it in a second building. And that's the reason why we have this notification that resource will be replaced. And it is actually very, very important to keep this in mind in the future when you work with your configuration, especially when something which runs in production with your user, with the data of your users. You should avoid the situations when, for example, you change something in your database settings and entire database goes away because it was recreated and moved to the different availability zone, to a different data center, right? So there are disruptive changes and non-disruptive changes. This change is disruptive. This means you should think twice before allowing to run it. So, and in our case, I will interrupt the apply and return it back to A. And actually, I started from the wrong number. It should be 10.0/24. And let me reapply this. Okay, cool. And as you see, it added and destroyed it because changing CIDR is also disruptive. It's not able to just to just alter it. It should delete it and recreate it. And here is the beauty of Terraform plan. It will always notify you in advance if it's gonna to destroy something or if it's gonna to create something or recreate something. So then next, let's make some additional adjustments and create the rest of our subnets. We need at least 3 more. So this one will be public 1, and this one will be public 2. Public 1, public 2. This one will have 10.0.1/24 and US East 1B availability zone. This one will be private 1, private 1, 10.0.2 and US East 1A. Why? Because each public subnet should correspond to the private subnet that's running in the same data center. So each data center should have everything that we need in order for these to be operational. And same here, private 2, 10.0.3, US East 1B. And name is private 2. Let's hit save. Let's run Terraform apply. This time, no, it's still suggesting us to destroy something. And that's really interesting. Why? Public will be destroyed, 10.0. Okay, yes, makes sense. We have renamed this one from public to public 1. And Terraform treats this as if we were to delete the old one and create new one. And this means like recreation. And later down the road, I will demonstrate to you how we can change this resource identifier without having to recreate the resource completely from zero. But not right now, not yet, just to make sure you guys not overwhelmed, because obviously we already have a lot of difficult concepts to grasp. And basically, let's hit yes. So this is expected because it tried to create the replacement subnet without having previous one deleted. We can either run Terraform apply again, or currently our configuration allows us to, if the error still persists, we could have just destroyed it, but you see it works good. Now we can create a thing called Internet Gateway. And there is a separate resource for that, and we can still go to documentation and search for Terraform AWS Internet Gateway. And that's the example of how we create our Internet Gateway. And we are just fine to have this basic example and install it basically like as is. Since it's called main and our VPC is also called main, it will fit perfectly well into this configuration and will be attached. Let's run Terraform apply. And hit yes. Also, for our resources to start working, we need a thing called route table. And same strategy here, getting back to documentation, and searching for AWS route table Terraform. This one slightly more complicated, but still copy this example, steal it, readjust, and it will work. So we don't need IPv6. We should call it, let's say, public. VPC should be AWS_VPC dot main. We'll have only one route, and it will be 0.0.0.0/0 into our internet gateway, AWS Internet Gateway. GW is not really best name for it. Let's make it consistent and call it main as well. And here should be also main, and here as well. And we need to connect our route table, same way as I showed on the diagram, to the to our public subnets. And this is done using a separate resource called route table association. Again, copy example. When you do it yourself, also take time reading all the parameters. Try to understand and make sure that you able to grasp them, or at least some of them. Table association. We'll have two. Public one, AWS subnet. Public one, ID, AWS route table. We need to point it to this route table, which is called public. And similar for our second subnet, public 2, public 2. So since route table lives in the VPC, spans entire VPC, we can have a single VPC, single route table per VPC, single internet gateway. Sorry, with the route table that points to it. Doesn't matter in which subnet we are using it, and we will reuse this this route table for both our public subnets. Let's run Terraform apply. Hit yes. And everything created. So this is the minimal configuration that we need in order to launch our public EC2s. So now we can go to AWS and launch our first instance. Actually our second instance. We've launched our first instance yesterday. We'll go to EC2. We'll press launch instance. Let's say public. I will pick Amazon Linux AMI. I will keep T2 micro. So I will use previously generated key pair, which I called main. If you don't yet have it, you can press create new key pair, and it will download everything you need to have, and you can add it either to PuTTY or to SSH. And if you need more help with that, when you'll be doing this, just send a message to chat. Me and Geoffrey will be happy to assist you. We'll change our network settings and switch into the main VPC that we've created and select one of our public subnets. It will also suggest us to create a security group. For now, we'll move forward and just create a single security group through this wizard. Later down the road, when it's time to automate EC2 instance properly, we'll also automate security groups as well, but not right now. So, and in security group rules, it's like firewall, from which IP addresses on each protocols and ports we can connect to. We can do SSH, for example, from my IP address, and Amazon will automatically calculate your public IP address of your internet provider, and provide it for you. The remaining details are irrelevant. Let's launch our EC2 instance. And I forgot one more thing. I forgot to associate public IP. So we can use public IP, we can use elastic IP. They are very similar, but except minor differences, and we don't pay attention. We will not pay attention right now. Let's also allocate, and over here in this tab, network and security, let's allocate an elastic IP address and associate it with our instance that we just launched. This means we can then copy this IP address and connect to it. So let's start with simple things. Let's get back to instances. And in addition to SSH in my security groups, I will also open ICMP, which will mean we'll be able to also run ping commands, for example. So now what we can do is go to our instance and copy its public IP address, get back to our terminal, and run something like ping and the IP address. This means it is available via network. This means it is replying to us. Also, we can establish secure shell connection to it, SSH. Basically, for those of you who are unaware, SSH is a protocol for remotely controlling your usually Linux box in a secure manner through the network. So we can run SSH ec2-user at IP address -i and the location of your key. This key is something you'll download when creating. We will press yes. And here it is. We are inside our EC2 virtual machine that we have deployed in our custom VPC. What we need to do next is complete the rest of the configuration. This is, first of all, two private route tables, and we will need to associate these route tables with our private subnets. And yeah, before we create route tables, obviously, we need NAT gateways, because we won't be able to assign public IP to something that should be run in private instance, right? So let's go and see AWS NAT gateway, and of course Terraform. So we need of them to be not one. I'd rather call it main. Main 1. And main 2. For subnet ID. Rule of thumb. NAT gateways should be, even though they're serving private subnets, NAT gateways should always run in themselves, should run in public subnets. Public 1, public 2. Our private subnet will connect to NAT gateway that runs in public subnet, and this NAT gateway will translate the request and will talk to the rest of the internet on behalf of this box. Also, it has this allocation ID. And as I mentioned, NAT gateway also requires its own public IP address that will be reshared across all of our private instances. And it is created using the separate resource. It was the elastic IP address, very simple. And we also need 2 of them. 1, 2. And this one we'll call it NAT1 and NAT2 because we need to highlight that they are assigned to NAT. We don't need this. We don't need this. And here, instead of example, it should be correspondingly NAT1 and NAT2. Let's exit from our public instance for now and run Terraform. Why? One more time. Internet gateway example. Yes. Actually, let's keep this. And it will take several minutes for NAT gateway to be created. And while we are waiting, we can use this time to to discuss and ask questions if you would like. Anyone, anything, maybe even related to previous class? Yes, Sanjeev.
Okay, hey Vladimir. So the NAT gateway will be a target for the private subnet route table, correct?
Yes, it is correct. And we will add them just after NAT gateway gets created.
Do we have like a cheat sheet to have this relationship like in a couple of sentences or like a flow chart, what depends on what, or just remember, right? For somebody who knew.
Yeah, I will share the diagram with you. And you can refer the code that I've written during this session. And if you'd like, you can create these cheat sheet for yourself.
Okay.
But that's basically what I'm explaining right now is the very foundational thing that every AWS engineer should remember this. And everyone has its own cheat sheet in a shape or form. And somewhat this quote when you're confident in Terraform, when you can read Terraform good enough to understand it fluently, this will by itself describe what it's there, right? And you already have a link to my repository, or otherwise you can scroll through our chat and find that where I'm committing to, and you can always refer to this.
Okay, thanks.
Okay, yeah. So let's move forward. Create our private route tables. We need 2 of them. Private 1, private 2. Let's immediately associate them using route table association resource. Private 1, private 2, private 1, private 2. And these should point to its own dedicated private 1 and private 2 route table. And instead of internet gateway, it should point the same route, but this time to NAT gateway. NAT gateway ID, AWS NAT gateway, main 2, and same here, AWS. AWS NAT gateway, main 1. And let's rename our let's name them correspondingly and run Terraform apply one more time. Hit yes. Very cool. Let's review what we have in our AWS user interface. We'll go to VPC. Here's our VPC, right? We can go and search our subnets, public, private. In our subnet view, we can expand it and, for example, see which route table is assigned for it and what it means. It will go to the smallest address first. It will check that, okay, 10.0.0/16. If the destination of the networking packet has this IP address, this means local. This means this request, this packet should stay within a VPC. Otherwise, all other addresses, the 0.0/0 means essentially entire internet should be redirected to our NAT gateway. And how would we verify that? We could launch one more EC2 virtual machine. This time, we'll call it private, and we will start it in our private subnet. VPC main, private 2. I will select existing security group that I've previously created and launch this instance. And also later down the road, again, we will talk about this more. But right now, I'll adjust the security group the firewall rule in our security group so that we can use SSH. Actually, no, we can use all, we can open all traffic for requests within our private VPC range. So, and when we SSH using our public instance and jump into our VPC, we can, for example, ping using our private IP address. So let's go to our instances. Here is our public, here is our private. It does not have public IP and it should not have, but it has private one, 10.0.3.79. And we can ping it using this IP address. And you see our public instance fits in the same VPC as our private one, and they can talk with each other. We can even, for example, SSH to this instance. Again, we've kind of jumped into our VPC through public IP, through our public instance. It's kind of like a window for us. And from this instance, we can safely navigate and connect to any IP within this network. It says, do you want to continue? Yes or no? We press yes. It returns permission denied because we don't have our key yet. Let me do some SSH magic, which is called SSH agent. And unfortunately, we're running slightly out of time. And I think this will be your home task to find out what these commands mean, how to use this SSH agent, and why after SSHing using this -a option, I am now able to SSH to this instance just fine. And you can see that right now, and if we run, for example, hostname, it will give us exactly this internal EC2 hostname of this internal instance. And to verify that it is able to connect to internet using our NAT gateway to make sure that our private routes are working, we can run something like yum update -y, and we need to make sure it is, we run it through sudo and make sure it is working. It says nothing to do. Okay, let's install something. Yum install -y, for example, links. Again, forgot sudo. See, installation started, and who knows what is links?
It's a command line web browser.
Very cool. Exactly. So what we can do is do links, google.com. Always. Yeah, don't expect experience similar to Google Chrome, but here it is. You can navigate directly from your command line, read some. Is it the site itself or not? Let's install one more thing. Probably it will give better interface. There is also e-links. Okay, very cool. Looks significantly more similar, right? This time. Here it is, Google. I'm feeling lucky. I have troubles navigating these tabs. I'm not that good at e-links, but just enough to make sure that internet is working on this instance. Let's exit everything. Now, last but not least, don't forget, add everything. Emit. Push. And on GitHub, create a pull request. And here is the thing. It might be at this point overwhelming, and it is completely okay, especially if you have just started. So what resources you will have to better grasp it? In the Trello card, there will be additional resources that you can go through. I will now share these pull requests for today. So you can see by example, here is the for our today session. And obviously, there will be recording available through Google Drive in this chat and also uploaded to YouTube to this channel. Let me immediately bring it up. The latest session, the yesterday ones, is already there. And to point precisely, and thank you, Boris, for jumping in once again. This is extremely appreciated. Let's help each other out and build this community. Yeah, raised hand, Ahmed, feel free to ask.
Sorry, it was a mistake. I was going to say thank you.
Okay, no worries. And one more thing, never forget to destroy your resources. And since we created a bunch of instances manually, you should go to Web UI and manually terminate them. Make sure you do this. Otherwise, you won't be able to run Terraform destroy. And never forget to run Terraform destroy. Extremely important. Because we don't want to get charged for what we are not using. This concludes today's session. I will stick around for 5 more minutes in case you have questions. Otherwise, see you tomorrow.